Hello everybody, thank you for joining me. Root Beer here with question number 3 on the 2013 Hypatia paper. Okay, hopefully you've downloaded a copy of the contest by clicking the link in the description and tried this question out for yourself. If you're ready, grab yourself a pen or pencil and let's dive in. So, question 3. A sequence of m p's and n q's with m greater than n is called non-predictive if there is some point in the sequence where the number of q's counted from the left is greater than or equal to the number of p's counted from the left. So if you're aware, this is sort of like ballot theorem. I can't remember whose ballot theorem. I want to say Bertrand's ballot theorem. But it's sort of like counting who voted for P and who voted for Q. If you're counting ballots in the photo in the after voting's been done in an election, and you keep counting enough P's so it looks like he's always winning, you get sort of that's sort of what we're talking about here. Anyway, I don't remember everything about the ballot theorem or any of that stuff, and likely it won't be necessary to do. But if you're interested, I think this type of sequence that they're talking about, Google ballot theorem, and you might be surprised at the theory you find. Anyway. So here's an example. If m is 5, so 5 p's, 2 q's, the sequence pp, qq, ppp is non-predictive because in counting the first 4 letters from the left, the number of q's is equal to the number of p's. Okay? So at some point I can chop off some amount and there's either a tie or more q's than p's. I would think that means that the no. I thought I had a thought, but no. Okay. Also, the sequence QPP is non-predictive because counting the first letter, you get a Q. So I guess to be predictive, you have to have a P at the start. Interesting. I'm guessing just based off the definition of non-predictive that maybe we'll have to define a predictive sequence at some point, and it might be something easier to do that with that then. Okay, so we got 3 parts to this question: light bulb and 2 writtens. If m equals 7 and n equals 2, determine the number of non-predictive sequences that begin with p. Okay, so we have to have the p first. You can't have one of these ones with q first. Okay. So we're asked for the number of non-predictive sequences. Are we having to figure out numbers? Number of non-predictive sequences down here. Number of non-predictive sequences is referenced again. So it seems like calculating the number of non-predictive sequences might be important. And I'm guessing that perhaps one way to count the number of non-predictive sequences is to count the number of sequences overall that have MPs and NQs and subtract off maybe the predictive sequences. Maybe. I don't quite know, but that's just some thought that's popping into my head based on the definition and the fact that it's non-predictive. Why don't we just define predictive? Well, we'll see. Let's just jump in with the light bulb. It shouldn't be particularly hard. I mean, we are told that we have to have a P right away. So let's jump into our notebook and it's a light bulb, so we don't actually have to write anything out. So let's just work this out. So we have P, and then we've got, what is it? It's M is 7, N is 2. So that accounts for one of the, so we got 6 P's left to go, and 2 Q's, and we need this to be non-predictive. Now, if we go P, then no matter what we do, we'll only have 2 Q's left over to be somewhere in here. The number of Q's will never be equal or more than the number of P's. So we definitely can't go P, but we have to start P. So what can we do after this P? Well, we could have another P, or we could have a Q. And as soon as we have that Q, we're done because then it's non-predictive. Then we've got a tie. The number of P's is equal to the number of Q's. And so then what's left is just count the number of sequences with 6 P's and 1 Q, and we don't care about the order. So that's 7 blanks and 1 Q to choose. So it's 7 choose 1 if you know binomial stuff, but you can just see it's going to be 7 sequences. So we got 7 sequences that start PQ. So there's 7 of those. Now if we went PP, in order for it to be non-predictive, we would then have to go QQ. No other way, because if we had a P here, we'd be done. We would never get to have a non-predictive sequence. So then it's the number of sequences, and our 2 Qs have been used, 2 Ps, so we've got 5 Ps. Well, there's only one of those, so PPQQ, and the number of those is 1, so in total there are 8 non-predictive sequences. Okay. So we don't really have to explain it, although if I were going to explain it, I would probably use my chart, or sorry, sort of my flow diagram, and probably better explain with sentences how I know, it's going to be 7 here and 1 sequence here. But other than that, we've got our answer. Okay. So that's A. Before we flip the page, let's actually read B. Suppose that n equals 2, just like in the last case. Show that for every m greater than 2, the number of non-predictive sequences that begin with P is equal to the number of non-predictive sequences that begin with Q. Interesting. Well, based on what I did in A, as long as I explain it, I think I can generalize it to count the number of non-predictive sequences that begin with P. Now, as for the number of non-predictive sequences that begin with Q, well, if you start with Q, by definition, I mean, they even gave it to us in an example. If you start with Q, automatically you're a non-predictive sequence. So, I can have Q and then anything. So I'll have Q and then I'll have m P's left and 1 Q. So yeah, I think just counting both of those will do just fine. So I might say something like, if we start with Q, we automatically have a non-predictive sequence. Sequence. Okay. So any arrangement of the MPs and remaining Q will suffice. So we'll have Q, and then we can have, so you can have Q, P, P, P. You can have P, Q, P, P, and then you can have P, P, Q, all the way up to P, and all the way down to Q at the very end. I would say it's pretty clear that there are m plus 1 such sequences. So there's m plus 1. And look at what we had last time. I mean, we did non-predictive sequences starting with P, and m was 7. We got 7 plus 1 such sequences. Okay. If we start with P, then either we start PQ blah or PPQQ blah, as there are only 2 Qs. Okay, so these guys don't share any sort of start, so there's no overlap. So we just need to count these numbers. The number of PPQQ is 1, as we just follow it with the the m minus 1, no, m minus 2 p's. Okay. Now if we start PQ, PQ blah, we can allow any arrangement of the remaining, hey, say I think I wrote this, and I also made that same typo, but of the remaining m minus 1 p's and 1 q. There are m ways to do this, and you could probably draw them out again just like we did with the m plus 1 ways to do it, but I'd say you do it once, you're fine. So the number of non-predictive that start with q, we saw as m plus 1, and the number that start with p is m plus 1. This for the one that start pq blah, and this for the one that start ppqq blah. So that's all that we needed to do. Okay, we did exactly what B asked us to do. We just computed the number that start with Q one way and computed the number that start with P another way. I'm guessing there might be some nice way to maybe bijectively, find a way to take a unique sequence that starts with P and turn it into a unique sequence that starts with Q. But nothing's immediately coming to mind, and I didn't need to do it, so why bother searching to make my life harder? Okay. Now let's take a look at C, the very last one. We still need to write this one up. Determine the number of non-predictive sequences with m equals 10 and n equals 3. Okay. So I can start with Q. And then so here's what I'm thinking. Either I start with Q, and we work that one out, or I start with P. So question B got me thinking about starting with Q, starting with P. If I start with P and I'm non-predictive, eventually I'm going to have an equal number. They say in the definition it needs to be equal or greater than number of Q's. But, suppose I had something like this. Well, I chop it off appropriately. I'm going to get an equal number of Q's. And I think I can make an argument like that. In which case, since I've only got 3 Q's, I either start off like this, or like this. And I know how to do each of those. Now this one is just going to be 7 P's arranged, so there's one way to do that. This is going to be 8 P's, 1 Q. And so we've already seen there are 9 ways to do that. This one might be a little more challenging, because we'd have 9 P's and 2 Q's. And I suppose I could bring in combinatorics, because that's just going to be 9 choose 2. And this one up here is going to be 10 choose 2. But do I really want to be doing that, or is there maybe a faster way to do this based on maybe some of the other numbers I've used? We got our result from B part. Is that just going to get thrown off on the side? I don't know. So I'll think about it for a second. But, I mean, if you've got a plan of attack, you go for it. You only have an hour to do this contest. So because I was wondering maybe is there a way to sort of build up with our definition, like let let Pn be the number of non-predictive sequences that start with P of length n, and Qn be the ones that start with Q, and then because then I could add anything onto the end of one of these ones, and I can really add anything onto the end of one of these ones. I don't know. I think there might be some merit in that, but I don't want to develop it. I don't want to waste time, so I'm just going to go ahead and do this. Okay, so we claim any a non-predictive sequence either starts with Q or at some point the number of P is equal to the number of Q. For some initial part, and you could make a more bold sentence, but okay. So suppose we don't start with Q. But after, within the, no, let's not say it that way. Suppose we don't start with Q. Let K be the minimum number of letters in to have the number of P be less than or equal to the number of Q, because that's the actual definition. We're just going to suppose we don't start with Q. So K can't be 1, because we're saying we don't start with Q. And consider the kth letter. If it were P, then we could use K minus 1 as only the number of P goes down. Actually, I'm going to rewrite this slightly just so it makes more sense, because I do like showing you guys better practices. I want to make myself exact, so I'm going to let PK be the number of be the number of P by the kth letter. And Q sub K equal the number of Q's that we get by the kth letter. Okay, so I already use M and N, and I'm using K in a very generic sense here, so I'm going to let R equal the min K so that PK less than or equal to QK. Okay. Now, since suppose we don't start with K or with Q. So R is not equal to 1. Okay. So if the rth letter is P, then PR minus 1 is PR minus 1, which is less than PR, which is less than or equal to QR, which is going to be the same as QR minus 1. So our rth letter is not P. Therefore, it is Q. Okay. Suppose PR is not equal to QR. Then PR is less than QR, but PR minus 1 is equal to PR, because when we go back a letter, we don't lose any P's. QR minus 1 is equal to QR minus 1. So PR minus 1 equal to PR, which is less than or equal to QR minus 1, which is equal to QR minus 1. But this can't happen because then there'd be an even smaller r that works. So by minimality of r, we have PR is equal to QR. Notice this would fail because we're assuming that we do have a letter to subtract from our count. And so it's clear we needed to have r is not equal to 1. Okay. So we've proven our claim. Either we start with Q or at some point we have an equal number of P or Q. Okay. So, being that we have Q blah or equal number P and Q, either we start PQ blah, PPQQ blah, or PPQQ Q blah. Okay. If you wanted to, you could explain these more. Having an equal number of P and Q means that you'll have to, so K is equal to PK plus QK, by the way. And so if that's equal, then K is even. And you can get a whole bunch of these that start PQ and then PQ, PQ, but if R is minimum, then you're only really going to get the PQ there that you care about. Or you have PPQQ or PPPQQ. If you want to explain it, I think it's clear. If it were more a situation where we have any number of Q's and any number of P's, you might want to better explain this, but I think it's fine the way it is. Just the short list. Okay. Let's get to the actual calculator. So Q blah, there are 10P, 2Q left. And any sequence after this first Q will do. So how many are there? Well, you could say 10 choose 2, or you could do a counting argument. 12 choose 2. 12 choose 2. Because there's going to be 12 spaces left out. And so you can choose 2 of them to be the Q's and the remaining 10 to be P's. So in terms of calculation, you have factorials here, but really what it boils down to is 12 times 11 over 2. And this is something that you could work out by, doing examples. So if you had 1 P and 2 Q's, for example, you could have P, QQ, or you could have QPQ, or QQP. What if you had 2 P's and 2 Q's? And you can so this one will be 3, this will be 6, and the next one will be 10. You can quickly generalize from there if you need to. But I think using the combinatorics, the choose notation, it's a grade 11 contest if you don't know that stuff. I strongly encourage you to binomial coefficients. But I'm not going to dwell on it right now. Okay, I want my calculation. So if I have PQ, there are 9P and 2Q left. And any sequence will do, so that's going to be 11, choose 2, 11 spots after the P and Q. So that'll be 11 times 10 over 2. So this one here is 66, this one here is 55. PPQQ, 8P, 1Q left. We've already seen there are 9, it's technically 9 choose 1, but that's really just 9 ways to do this. PPP, QQQ, blah. So only 7P left, so that would technically be 7 choose 0 Qs. There's one way to do that. So we add it all up, 66 plus 55, that's going to be 121, because it's 11 times 6, 11 times 5, 6 plus 5 is 11, so it's 11 squared, plus 9 plus 1, so 131 such sequences, so non-predictive sequences. Okay. So the reasoning's all fine. If you wanted to count these in a different way, that's fine. Heck, if you came up with a different solution, that's great too. I'm under the impression that when they write up solutions to these papers, they do try and avoid using things like binomial notation because they know not every high school in Canada by grade 11 has seen it. So I'd be interested to see if they had a different way to count these, even if they broke it down the same way I did, or even if there was a different way to break the problem down. Maybe, as I said, there's a nice recursive definition. I don't know. If you had a different way to do it, I would love to hear about it. But other than that, that's question 3, and I'm going to move on to question number 4 in the next video. So I will see you guys then.